I am recording. Great. Anyway, so I want to have some office hours because of the test, because I think that rather than have people really struggle with not even knowing, where to find things or get started, I'm willing to have some of these office hours like I did last time. And the test is going to be emailed either tonight or tomorrow morning, and it's due the following Thursday. And I'd like to put some office hours down for, later this week, but also, hold on, Friday afternoon, I got that. And also even over the weekend, if that's convenient. So somebody requested Friday afternoon. Now Friday, I can't do it until after 2:30 because I go swimming, but I'm willing to do it Friday afternoon or Friday evening. I just would like to know what's good for people. So, Saturday would work. You know what I'm going to do? I think I'm going to stop sharing this screen, and I'm going to put up the, I think I can put up the, how do you do it? Oh, share screen. Yeah. The whiteboard. Okay. So, and I think you can write on it with your mouse. Oh, actually, oh, I know what I got it here. I got my other pen, my other tablet. So we have Friday. Let's see. Oh, look at that. How did it know to do that? We have Friday, so I could do it like 3 p.m. Is that good for a bunch of you? Got Saturday. Also Thursday of this week. So can you write on this or type on it? 3 p.m. Sunday. That sounds good. But I want to make sure that it's more than just one person. Oh, I like that little check mark. Okay. Anybody else? Not, okay. I like that Friday. Good. Did we have a time for Saturday? Was that 3 p.m.? Did somebody say what time on Saturday? Just turn on your mic and just say it.
I can do any time in the afternoon or night. I just work in the morning.
Yeah,
Okay.
afternoon would be nice.
Some people work Saturday and would like it after they work, so I could do it at 6 or at 7 or at 4.
I think 6 sounds good to me. I don't know if that works for anyone else.
Okay, 6. Is that bad for some who wanted to do in the afternoon? I could do 2 hours. What about other days? Well, listen, folks, if I'm not getting a lot of feedback, I don't quite know what to do. So it'd just be nice to have some of them. I got some Friday feedback. That's great. Saturday at 6 sounds good. All right. So we'll leave it at that for now. If you want, if somebody wants to email me, I'm perfectly open to that. Would you like me to do? I think I should do a Sunday. What if I did it Sunday at 4? Does that look good for anyone? Want to put a check mark there? If you
That could work for me too.
Yeah. Saturday at 6 is kind of like supper time for us, but we sometimes eat at 7, so it doesn't matter. I guess I could do it at 6. It doesn't really matter.
I could do 5 or 7 too. It doesn't really matter to me as long as it's later.
Yeah. But some people wanted it earlier on Saturday. So how about if I do Saturday at 2 and 7? How's that sound?
2 p.m.
What about Sunday at 4? Anybody for that? Okay. Well, all right. That's what I'm going to do. I'll write that down. I don't know. It didn't sound like there was a lot of enthusiasm for that, but I know people like to leave exams for later on, but I don't recommend that. This exam is going to take a while to do. and like I said yesterday, I consider that the exam, doing it is like the studying and the doing of an exam. That's why, it will take a while, and don't just start it. Don't start it on Wednesday next week and expect to get it done. And I really, if people are going to hand it in late, they need to contact me. Okay. You can't don't just do it. You have to, get me on board with that. Okay. So, all right. Now, all right. Let's go back here. Oh, I have a bunch of chats here that I haven't read. Look at that. Oh, is Sunday, the person who said Sunday at 3, could they do Sunday at 4? I am going to put those times on Blackboard. Okay. Okay. All right. Well, all right. It was a little better than I thought, the response. Okay. So listen, if you didn't get a time that you wanted, send me an email and maybe I can make another time just for you, or people. And I'm going to put these up on Blackboard so everyone will know. Some water. All right. So. Something else about the exam. Okay. So what I did was I accumulated a bunch of equations. I'm going to send out this information sheet with the exam. It doesn't have every equation you'd ever have to use, but it has a good number of them. All right. And another thing I did that I have absolutely never done before is this. Okay. I actually made an index. Do you understand what this is? This is telling you for every question on the test where to find information on that in the notes. I'm trying this out. I've never done it before. You may all get 100 on the test because that, maybe this is all you need is to look at the notes. What I'm trying to do is I'm trying to get you not to just go randomly to websites on the internet, which most of the time I think they're not that helpful. Yeah, thanks. You're welcome. I honestly think that I don't care if everyone does well on this test, but I want people to work on it. And I want to give you the tools to work on it and be able to be successful. So rather than asking you to write the index, which I think I did at one point, maybe last semester or last exam, I decided to write it for you. So okay. What I would like you to do is that if you use my notes, that you say that you use the note, that you tell me what you used, just because I'm actually thinking this is an interesting experiment and I'd like to have some data. Okay, so that's really all that I would ask. That's really too much trouble. Then you could still use the notes. Just it would be nice if you told me that you did use that particular problem. All right, so we have I'm very excited because we get to a really, really important topic today in chemistry. And, I told some of my students in lab last time that my field is physical chemistry, and that I actually love all the workings of mathematics into chemistry. And I love the topics like equilibrium and kinetics, and where there's great ideas, but there's great mathematical ways of thinking about it too. But anyway, not to scare you, those of you who are scared of math, but I just want you to know that this is very exciting to some people like me. So anyway, I'm going to move on from all that and tell you that this next topic, my pen is so fat. On. God. My computer's being a jerk. Okay, equilibrium. Yeah, so this topic is a new topic. This is Unit 5. I'm going to have to put the homework up, but I know you have an exam coming up, which is on Units 3 and 4. But yeah, please at least come to class and try to take in what's being done. So I'm going to start, oh yeah, this unit is great because it talks about how reactions don't just go forward. So the way I start this off is say that reactions go forward and back. Okay, so here's an example of reaction. I'm actually not even giving you the full Lewis structure of this. I'm just kind of showing you the bonds, not even whether they're single or double or anything. And this reaction, like all chemical reactions really, comes to an equilibrium, which I'm going to tell you what that means. So what this really is N2O4, one of them, forming two NO2s. And this actually happens in the gas phase. And one of these, I believe it's NO2, has a brown color. So you could see the appearance of it. Well, anyway, what this reaction is it's a simple breaking of one bond. Okay. And it's actually, we just finished the kinetics unit. This is an elementary reaction. What does that mean? What does it mean for something to be elementary? The way I like to say it is that it occurs as written. In other words, there aren't a whole bunch of steps that get added up to make this happen. It is a simple, single chemical event. It occurs as written. One bond is broken basically, and it forms products. Okay, so it's an elementary reaction. Now, if we were in Chem 103, which wasn't that long ago, right? So in first semester Gen Chem, if I told you that we had 10 moles of N2O4, and I ask you what's present at the end of the reaction, what would the answer be? What's going to be present at the end of the reaction for Chem 103? You start with 10 moles of N2O4. How many moles of NO2 do you end up with? I thought that beep was somebody beeping like on Jeopardy to answer the question. 20, exactly. 20 moles of NO2 at the end, right? Okay. But now we're in Chem 104. And I will tell you that that is a lie. That is a bald-faced lie. That reactions really don't do that, many of them. Some of them go very far to the end, but this one doesn't, okay? And many of them don't. That's not always how reactions work. So what actually happens here, and for most reactions, I would say most reactions end up somewhere in the middle. So if you start with 10, it'll go for a while. Maybe you'll get 15 moles. Let's make it even because it's double. Maybe you'll get 16 moles of NO2, but it won't go to completion. And in Chem 103, it's all about going to completion. That's all we teach you in Chem 103 because we save the good stuff for Chem 104. Okay, so I'm going to launch into this equilibrium topic by saying that with this particular reaction, you start out with all reactants, and yes, you get some products forming, but at some point, no more products will form, even though there is reactant left over. That point is the equilibrium point. All right, so I'm going to show you, I'm going to use some information that we learned in the last unit to sort of bring this point home. Okay, so I'm going to say if we start with the N2O4 only, that's all we have in the flask. Okay, and if you think about this reaction, and I ask you, what's the rate? So we say there's a forward reaction and there's a reverse reaction. And they both have rates. Okay, so if we start and we have only N2O4, we have 0 NO2 at the beginning. So I'm going to ask you this question. What is the rate of the reverse reaction at this point? So let's think about that. Okay, remember I said this is an elementary reaction. That means it occurs as written. That means we can look at it and we can write the rates, both the rate of the forward and the rate of the reverse. What's the rate of the forward reaction? And the reverse reaction is 2 NO2s coming together. So there's 2 reactants and they're both NO2. What would be the rate of the reverse reaction? If you have 2 NO2s, the rate, because this is elementary, so I can look at it and write the rate law. The rate of the reverse reaction is a rate constant times NO2 squared, right? Because 2 NO2 is like NO2 plus NO2. So we end up with the rate being proportional to the concentration raised to the power 2, because there are 2 of these on this side. While we're at it, let's write the rate of the forward reaction. So what's the rate of the forward reaction going to be? Anybody in the chat? I don't see anyone answering that one. But we have only 1 mole of something on this side. If it's an elementary reaction, it occurs as written. What do I put in? Yep. What?
It's just N2O4.
Exactly. Now I'm going to call this the rate constant for the reverse reaction. And this I'm going to call the rate constant for the forward reaction. These are different. And you could see from a simple diagram why they would be different. This is the activation energy for the forward reaction. This is the activation energy for the reverse reaction. Since there are different activation energies, there will be different rate constants. So that's why I call 1 Kr and 1 Kf. All right, so let's go back to the rate of the reverse reaction. We have a situation where we have 0 NO2 at the beginning. We have only N2O4. That means this concentration is 0. So initially, there is no reverse reaction happening. The rate is 0 because there's no NO2. It can't go in reverse because it doesn't have the ingredients it needs to go in reverse. So there is no reverse reaction initially. But what happens as time goes on? As the forward reaction happens, the concentration of NO2 increases. So what happens to the rate of the reverse reaction? Does it increase or does it decrease? As you keep making more NO2, you're increasing this concentration. You're increasing the rate from 0. It's going to increase. Remember, rates depend on the concentration of reactants, and the reverse reaction has NO2 as its reactants. Okay, if you're going in reverse, these are the reactants. If you're going forward, this is the reactant. Okay, so the rate of the reverse reaction increases as the reaction goes on. Well, what happens to the rate of the forward reaction? This is the rate of the forward reaction. What happens to the rate of the forward reaction as the reaction goes on? So as the reaction goes on, the concentration of N2O4 drops. It's being reacted away. So actually the rate of the forward reaction decreases. It starts out with only forward reaction happening because there's only N2O4. As you produce NO2, now the reverse reaction starts happening more and more. So as the reaction goes on and the reactant N2O4 drops, the forward rate drops, just like with any reaction that we've studied. As the reactants get used up, the rate decreases. That's what's going on here. The forward reaction rate drops. So what we've got here is the forward rate is dropping. And that's because the reactant N2O4 is getting used up. As NO2 forms, the reverse reactions rate increases. So the forward rate drops. As the reaction goes on, the reverse rate increases. And so what happens at some point? So at some point, what do you think is going to happen? You got the forward rate going down, the reverse rate going up. At some point, they're going to have to be the same, right? One is going down and one is going up. At some point, these rates equalize. And at that point, and at all points further, you have the equal rates of forming reactants and products. So what does that mean about the concentrations of the reactants and products? If you have the equal rate of going forward and back, are those concentrations going to change? Yeah, the answer is no. From this point on, the concentrations of the reactants and products stays the same. There's still both reactions happening, but you don't get any change in concentration of those things. That's called a dynamic equilibrium. Dynamic means moving, really. It's a dynamic equilibrium because it's not like the reaction stops dead and doesn't go either way. It's that you get both reactions happening. So both forward and reverse reactions still happen, but at equal rates. So there is no change in concentrations after that, after equilibrium is achieved. So this is pretty strange. I mean, this is pretty cool stuff, really, once you grasp it, which, you know, if it's your first time thinking about a thing like that, it's pretty, it's not trivial. Let's just put it that way. Okay, so at some point those rates equalize, and this is what we call equilibrium. So when the system of forward and reverse reaction, when it achieves equilibrium, after that point, the concentrations don't change anymore, okay? This is happening at equilibrium. All right. So what I want to do is show you something, which I think is fascinating, but maybe you won't. The forward rate is K forward times the concentration of what's reacting, which is N2O4. And the reverse rate is K reverse. By the way, we use small k's for rate constants. When we use an equilibrium constant, which we're going to get to, we use a capital K. But this is the reverse rate, second order in NO2. This forward rate is first order in N2O4. At equilibrium, right? These become equal. And here's what you can do if you just do a little bit of algebra with this. If I move the N2O4 to the other side, so in other words, I divide both sides by the concentration of N2O4. So this cancels. And then I move my Kr to the other side by dividing both sides by Kr. So this cancels. So what I end up with is this K forward over K reverse equals the concentration of NO2 squared over the concentration of N2O4. So if you remember, you know, the reaction was N2O4 goes to 2NO2. So what I basically got here is the concentration of the reactants here squared. I'm sorry, the products of this reaction over the concentration of the reactant. And look at this. This is a ratio of two rate constants. Now, rate constants, for a particular reaction, they're constant as long as what doesn't change, as long as what parameter doesn't change. Remember, we did in lab, some of you yesterday, we saw that the K, the reaction's rate constant, depends on temperature. Yes. So I guess I would write here, as long as temperature is constant, this ratio is constant. It does not change. So that means that once you get to equilibrium, the ratio of the concentration of NO2 squared over the concentration of N2O4 doesn't change. And because it doesn't change, we call this ratio K equilibrium, but we also call it KC. K equilibrium is kind of a general term. KC is for concentration, because sometimes we have things other than concentration in the ratio. So generally I call it the equilibrium constant, but it's the KC equilibrium constant because these are brackets here and the brackets mean molarity. And so we're doing it in concentration. We could do it in pressures or different units, but we call it KC. So this KF over KR is the equilibrium constant, okay? And it doesn't change once you get to equilibrium, once equilibrium is reached. From that point on, this ratio of NO2 squared to N2O4. Now, if we look at this equation more closely, right, we look at this, you notice that 2 here, that the power that this is raised to is actually the stoichiometric coefficient of that product. And the power here, which is 1, it's not showing, but it is the stoichiometric coefficient of the reactant. And that's not a coincidence. That's not an accident at all. So KC or KEQ is a ratio. Remember, a ratio is something divided by something else. It's a ratio of the concentration of products over the concentration of reactants, each raised to the power of its stoichiometric coefficient. Okay. All right. So let me show you. If you have a really complicated reaction, like suppose you have A plus B goes to C plus D, but you have all stoichiometric coefficients, I'll make little a the stoichiometric coefficient to A and little b the coefficient to B. And similarly, the equilibrium constant is the ratio of the concentration of C to the C power D to the D over A to the A and B to the B at equilibrium. So this idea that it's this crazy concentration ratio that stays constant at equilibrium, and it's got the stoichiometric coefficients as powers, that's completely general for any kind of crazy reaction. I could have N2 plus 3H2 goes to NH3 like that, right? And the Kc is NH3 squared over N2 to the 1, so I'm not going to write that 1, over H2 cubed. That this is constant once equilibrium is achieved. Okay, so it's totally not arbitrary at all. And here's the crazy thing, right? It doesn't matter what the initial concentrations of reactants and products are. You could start with all reactants, you could start with all products, you could start with the same amount of each, you could start with vastly different amounts of each. You will always, as long as the temperature is the same, you will always end up with this ratio, whatever it is for the particular reaction, being the same constant at the same temperature. So that's the beauty of it. And I'm going to show you a couple of pictures now. Okay, so I'm going to illustrate that no matter where the reaction starts, let me write that down. No matter what the initial concentrations are, for the reactants and the products, no matter where the reaction starts, in other words, you will always end up with the same ratio of these products over reactants to the powers of the stoichiometric, to these stoichiometric powers. So I'm going to show you some data, or really summarizes some data for the same reaction that we've been thinking about. Okay, I'm going to show you 3 graphs of this reaction where we start with all N2O4, all NO2, and then the same amount of N2O4 and NO2. So let me show you this. Okay. All right. So here are the 3 graphs. All right, so let me set the scene here. This is N2O4. This is the reactant, all right? In blue, we have NO2. This is the product, okay? So we start at the beginning with no NO2 and all N2O4. So we basically start here. That's the N2O4. The NO2 is 0. So what happens is the reaction goes forward because the reverse rate is 0. There is no NO2. It can't go in reverse. So what happens is that reacted concentration, N2O4 reacts away. You think, oh, it's just going to go away completely and be replaced by NO2. But then what happens is no. It gets to a certain point and it levels off. It just levels off. It doesn't go down to 0. And similarly, there's no NO2 at the beginning. Oh, you think it's just going to become all NO2 at the end. You know, if you're thinking general chemistry 103 thoughts, you'd think this would go all the way down and this would go all the way up, but that's not what happens. This goes up, and then at a certain point, it simply levels off. Okay. Here, we start with the same amount of both. And, I wouldn't really know which way this reaction was going to go. Here we have, again, the reactant, N2O4, and the product, NO2. All right. And it turns out that, look what happens is the reactant concentration actually goes up. And the product concentration goes down. So which way is that reaction basically going? If the product concentration is going down and the reactant concentration is going up, then the net direction is that way. Here, we're losing reactants and gaining products. So the reaction went forward to get to equilibrium. Okay, and now here, we started with all NO2. So since there's no N2O4, basically the NO2, the reaction is going in reverse. Okay. And what that does is it increases the amount of N2O4. And so eventually it levels off. And the same thing, this NO2 drops like a rock at the beginning, but then it levels off. All right. So you could see that each one of these concentrations levels off. Okay. That means it gets to a concentration and then it stops changing. It doesn't change anymore. Well, where has equilibrium been achieved? Equilibrium is achieved right about over here. That's where the concentrations stop changing. That's where we've achieved equilibrium. And then it stays at equilibrium. Here, it looks like it's about over here where equilibrium is achieved. Okay. So, but here's the crazy thing. If you formulate this ratio, this NO2 squared over N2O4, you see that I give you the concentrations that it ends up with. The NO2 concentrations, this one down here, 0.0100 squared over 0.0200. And if you figure out what that equals, it equals 0.00500. All right, that's what the equilibrium constant is, because that's the value of the ratio of these concentrations at equilibrium and beyond, right? Because beyond stays at equilibrium. It doesn't get into equilibrium and then go out of equilibrium. Once it gets to equilibrium, it stays there. Now here we had a completely different set of, a completely different starting point. They're both the same. They're both 0.0125 at the beginning. One of them goes up, one of them goes down. But at the end, if you find this ratio, it becomes 0.0087 squared over 0.0150. And guess what? It comes out to 0.00500. That's the equilibrium constant. Doesn't change. And here, my last example, when you start with all NO2, you end up with the NO2 concentration of 0.0070. So you have to square that over N2O4, which is also, wait a minute, I think, no, it's 0.0100. Okay. If you figure that out, it comes out to the same number. So this is amazing, and it's not like you do something to the system. You just let it sit there and it does it itself. You start with the same concentrations, you end up with the same Kc at the end, the same ratio. They're not, none of these numbers are the same. Look, 0.01, 0.0, my pen. My pen stopped writing. This hasn't happened in a while and I'm very annoyed. There it goes. Okay, so here you end up with an NO2 concentration of 0.01. It's totally different numbers here that you end up with. But when you put them together, I forgot a zero here. There you go. But when you put those different numbers in, it gives you the same ratio. And actually I have that here. So if you didn't copy it down, you can always look at it later. So you get the same number regardless of what the initial concentrations were. Okay, and that number is Kc, the equilibrium constant, or KEQ. So that, to me, that's amazing. It means that you could start the situation with that it means that you could approach equilibrium from either direction. You start with all reactants, it's going to approach, you're going to go to equilibrium. And start with all products, it's going to go to equilibrium. And the ratio of those concentrations will be exactly the same. Somehow the reaction does that. And that's what is kind of amazing. Anyway, that's what happens. So I want to take a closer look. Oops, not with that pen. At the first figure. So I want to look closer at this figure here. And that's what the next slide looks at. Okay. Okay, so down here we go. I'll put an arrow. All right, so this is just the first graph that the one that I just showed you. And I want to show you what happens, not just when you get to equilibrium, but as equilibrium is approached. Okay, so this is again, our reactant concentration here. This is the reactant. Oh, I wanted this in the same place, but of course it didn't work that way. There we go. All right. So there's reactants and we have the products. Okay. And at the beginning, we had all N2O4 and 0 NO2. All right. But then the reaction started. But what I want to do is figure out what is that concentration ratio at the beginning. So that's what this is here. You'll notice that. So we use Kc is what the ratio of those concentrations is at equilibrium. But you can actually formulate that ratio anytime during the reaction. It just won't equal the equilibrium constant. Qc is that ratio of concentrations at any time, not necessarily at equilibrium. And so at the beginning of the reaction, you have 0 NO2. So I'll put a 0 here for it, and I'll square 0. Squaring 0 gives me still 0. Okay, it doesn't matter what I divide by, but I'll put in what the concentration is, 0.025. But I get a 0 here, all right? That's at 1. At 2, a little bit further. So what has happened in the meantime is the concentration of N2O4 has gone down, and the product, the concentration of NO2 is going up, and I get to 0.2 in the reaction. And so now, instead of NO2 being 0, it's 0.0075. And I square it, and I divide by the concentration over here of the N2O4, which has gone down to 0.0213. And I get a number. This is the number. Okay, so you can see that this number has increased. And then if I keep going and I'm at 0.3 and I do the same thing, that number has gone up a little more. And finally, when I get to 4, and this is at equilibrium, I've reached that number there. Actually, I probably reach it right around here, but that's okay. At equilibrium, remember, that's the number of the equilibrium constant. And if I kept going, it will always still equal that number. But what happens is when this QC ratio is smaller and then Kc, the reaction goes forward. And it goes forward until the ratio actually equals Kc, and then it stops changing, right? The reaction goes forward until QC equals Kc. And at that point, the concentrations of the reactants and the concentrations of products stops changing. So we notice that when the ratio is smaller, okay, when the ratio is smaller than the equilibrium constant, the reaction will go forward. How do we think about that? Let's think about that a little bit. We have QC is NO2 squared over N2O4. This is at any time, doesn't have to be at equilibrium. It's equal to this ratio. If QC is less than KC, okay, that means that the numerator here is too small, or the denominator is too big, okay, for equilibrium. So what happens then is we want to increase, QC will increase to equal KC. So as N2O4 goes down, QC goes up. And that's because you're decreasing a quantity in the denominator, which increases the overall value if you're mathematically inclined, right? Or as the NO2 concentration increases, the numerator increases and the QC ratio will go up. But when does that stop? It stops when it equals KC. Boom. All right. So, so that's what happens when QC is less than KC. So I guess I'm going to write that down, that as long as QC, the value of it is less than the equilibrium constant, the reaction will go forward. And that's not just true here. This is true in general. All right. I know this is difficult. I do. You're going to have to study these notes. And maybe ask me about it if you can formulate some questions. All right. So what this now is the opposite situation. So I'd like to address here, what if QC is greater than KC? That's what's next. And that's what happened in the second diagram. So if we go back here, now I'm talking about this second diagram here, where they started at the same value, each of the concentrations. So this is that second diagram, all right? So if you formulate the Q, so in other words, you take the concentration of NO2 squared over N2O4. At the beginning, both of these are the same concentration, 0.0125 squared over 0.0125, it's 0.0125. That is greater than KC because KC was 0.0500. So 0.0125 is greater than 0.0500. Okay. So what happens? Well, what's going on here is N2O4 is forming and NO2 is going away. Well, remember, it's N2O4 is the reactant and NO2 is the product. So if reactant is forming and product is going away, then this reaction goes in reverse here. As it goes in reverse, more of the N2O4 forms. So the concentration of N2O4 increases and the concentration of NO2 decreases. N2O4 is in the denominator. The denominator increases, means the ratio goes down. So QC goes down. you could see that as the numerator's value is decreasing. So QC goes down. And when will it stop going down? Anybody? Stops going down when it equals KC. That's when it stops. And that's when this thing levels off here. All right. So all that I just said is actually written here pretty much. Well, not really. This is greater than KC. Reaction will go in reverse, decreasing the value of Q until it equals K. And at equilibrium, we have these concentrations. And lo and behold, the ratio is again equal to the same number. That's pretty phenomenal. Pretty strange. Getting cold again. All right. So equilibrium can be approached in either direction. It can be approached from forward or from reverse. It doesn't matter. It's going to be the same number as long as the temperature doesn't change. All right. So I'm going to show you another example without diagrams, but I want to look at a different simple reaction. We're doing all simple reactions. So here's a different but simple reaction. We take hydrogen and iodine, diatomics, these probably would be in the gas phase, and goes to form 2HI, okay? And the case, I'm just going to say that at some temperature, the Kc is 16. So I may have to find a very outlandish temperature to make that be the equilibrium constant, but that doesn't matter. So let's suppose we have a reaction mixture. So we have this going on in a, in one of these big old flasks with a valve here, and the valve is closed. And we have these reactants in there. And let's say that the concentration of H2 gas and I2 is the same, and it's 1 molar. So it's like 1 mole per liter, okay? And let's say that the product concentration is 4 molar. All right, so we got some simple numbers in here. So let's ask a question. Is this reaction at equilibrium? How do I figure that out? I have to write that ratio, right? So QC, I don't know if it's at equilibrium, so I'm not going to call it K. I'm going to say QC is, all right, the concentration of products, that's HI. What do I have to put up here? Two. Yeah, that's right. HI squared over, and here I just have H2, I2, each to the power 1, which means I don't have to write them at all. Okay, so this ratio, what is it? So we have that HI is 4, so 4 squared and 7 years ago, no, 4 squared. All right, over 1 times 1, so that's 16. So let's answer this question. Is this reaction at equilibrium? What's the answer to that? What you're looking to see is, does QC equal KC? If yes, then the reaction is at equilibrium. And it is. So this reaction is at equilibrium because that ratio equals 16. Good. All right. So now, what can you conclude? So you can conclude that the reaction is at equilibrium and it doesn't go up. So is at equilibrium, and it does not change any of the concentrations anymore. It means that the forward rate equals the reverse rate. So the concentrations stay the same after that. Okay. So now I'm going to throw a wrench in this little happy little equilibrium. So we have H2 plus I2 goes to 2HI. And we had, this is what we had, was that this was 1 molar and this was 1 molar and this was 4 molar. And we had that this was equilibrium. Okay, because the QC equaled KC, which was 16. So now what I'm going to do is I have this nice reaction at equilibrium, and I'm going to throw a wrench in it by changing. I'm going to add more hydrogen so that the concentration is 2 molar of hydrogen, but it's still 1 molar of iodine and 4 molar of HI. Okay. So my question is now, what is the Q? What is QC? So now QC is, okay, it's still the concentration of HI squared over H2 and I2. But now that this is still 4, so that's 4 squared. But this is 2 now, so it's 2 times 1. Okay. So instead of being 16, this is 8. So now the reaction is no longer at equilibrium. Okay. But we have QC is less than KC because KC is still equal to 16. So which way will the reaction go? Which way will the reaction go to make the QC equal the K? Remember, we have products on top here and reactants on the bottom. So yes, it will go forward. The reaction will go forward because that will increase the concentration of HI and decrease the concentrations of H2 and I2. And QC, here it is, HI squared over H2, I2. If you increase the concentration of HI, you will increase Q. If you decrease this, you will also increase Q. So both of these will increase QC until, when does it stop increasing? Come on, turn on your mic and tell me. When QC equals what? That's right. Until QC equals KC. Now, there's another way to look at this. So this is kind of looking at it mathematically. If QC is less than KC, you could see, since this is Q, that increasing the numerator, increasing the product concentration, and decreasing the denominator, decreasing the reactant concentration will change this Q, make it larger so that it will equal K. But there's another way to look at it that's actually probably easier. So here's the reaction again. So this is an alternate way to look at this. Well, these fans are not keeping up with the heat that this computer is producing. Okay, so an alternate way to look at this is that what we did was we added H2 whoa, situation, that reaction was at equilibrium. It was at a nice equilibrium, and you stressed it by adding H2. And if you remember Le Chatelier's principle, which we've talked about already, but here it becomes important again. When a system at equilibrium is stressed, it responds by moving in a direction to decrease or reduce the stress. Okay, so we're adding H2. This reaction can only do two things. It can only go forward or back, okay? When you add H2, the reaction, it drives the reaction forward. We say it drives a reaction forward by Le Chatelier's principle. The added stress, this reaction is getting rid of the stress, right? Getting rid of the stress is the same as getting rid of H2. And so the reaction goes forward. Okay. Let's see. So, there's really two different ways of understanding this. You can understand this by the fact that QC was less than KC. Wait a minute. Yeah, after you added that, so you increase the number in the denominator here, right? When you did that, you decrease the value of the quantity because that's mathematically what happens. And so mathematically, to increase Q again, you've got to produce more product and reduce the amount of reactant. And that means the equation goes forward, the reaction goes forward. Or you could look at it by Le Chatelier's principle. You added a reactant. That was a stress. The reaction responds by removing the stress. And the only way it can do that is to go forward. That's really, the reaction can't, it can't do anything but go forward or back. It's pretty constrained. Okay, well, let's think about another thing that you could have done to this reaction, this poor reaction. Okay, so again, let's say we have H2 and I2 forming 2HI. Okay. And let's say we're at equilibrium with 1 molar of each of these and 4 molar HI. That's what we had, that we turned out, we proved that that was equilibrium. And now what I'm going to do is I'm going to increase the concentration of HI. I'm going to make it 5 molar. I'm going to add HI and I'm going to leave these the same. So they're 1 molar, 1 molar, and this is what I have now. So I just added a product. So there's my Q. I added some HI. Oh, I didn't mean to cross it out. I thought I was highlighting it. So I added HI. That means I increased the value of QC. In fact, now it's 5 squared over 1 times 1, which is 25. When I increased it, remember the KC was 16, just to remember that. I increased the value of QC. So now QC is greater than KC because it's 25, which is greater than 16. So what do I have to do to concentrations in this ratio? What has to happen to decrease QC? So to decrease QC, I have to decrease the HI concentration and increase the H2 and I2 concentrations. Which way does that mean the reaction's going to go?
It'll go in reverse.
That's right. That's right. So the reaction will go in reverse. And you could see that mathematically by looking at the effect of changing the numerator and the denominator here. But you can also use Le Chatelier's principle. H2 plus I2 goes to 2HI. You add HI. That's a stress. The reaction responds by going in a direction to remove the stress, which is in reverse. Okay, so it goes in reverse. So you can use the mathematical way, QC here was greater than KC. So the reaction has to go in reverse. Or you could think about it in terms of Le Chatelier's principle. It amounts to the same thing, okay? All right, so those are both good ways of thinking about it. All right, so I'm just going to show you some handouts that I posted for this this unit. So this is the activities handout for Unit 5, but I want to point out something that I have never done in this class before. Well, I've done it in other years, but not in this class. I give out these sapling problems. What I did was I actually wrote which type of problem this is, okay? What sorts of things you have to know to do those problems. So you can tell which ones maybe you want to do first, the ones that, which ones you know how to do. And another thing I do in this unit is I give you the different types of equilibrium problems. I'm trying to organize the unit to some extent so that you can know where you're at, like what you know in this unit, what you're supposed to know, what we haven't gotten to yet, which of these are harder, which of these are easier, because there's a lot of different types of problems that you can do in this unit. So what I'm going to do is this is like that's the overall handout there, these 5 different types, but then I go through them, okay? And I do the easiest types first, all right? So one type of equilibrium problem you can be given is if you're given the concentrations of each of these reactants and products at equilibrium. We call those the equilibrium concentrations. So if you're given the equilibrium concentrations, you can find the value of the equilibrium constant. And sometimes by the way, I just call it K because it's K, it's KC, it's KEQ. All right. Notice it's capital though. We always use a capital K. Smaller K is left for rate constants and things like that. So, okay, what you have to remember here is the KC expression, right? You take each product, you raise it to its stoichiometric power, and then each reactant raised to its stoichiometric power. If you want to know why that is, you have to take PChem, Chem 405. All chem majors have to take it. I teach it, at least as long as I'm still at Rhode Island College. And it's fascinating how it comes out to be that way. But anyway, so here you're given what those concentrations are, and you're told that it's at equilibrium because you call them the equilibrium concentrations. That means at equilibrium. If they weren't at equilibrium, you couldn't call it that. You just say the concentrations. So you just take the concentration of NH3 here, 2.34 molar, square it over the N2, which is 3.12 to the 1. So I don't need to write that. And the 1.500 to the 3. Okay, and each of these is to 3, 6, well, one is to 4, 6. I don't know why I put that 500 there, but that's kind of weird. But anyway, if you do this on your calculator, and I actually recommend, I'm sorry, yeah, I actually think you should do this right now on your calculator and compare it to what I got, all right? Because there's a little bit of trickiness with some calculators when you have more than one thing in the denominator. Anyway, the number you should get is 0.520, and that is the concentration equilibrium constant, because these are all given as concentrations. So that's why we call it Kc. So that is a type 1 problem. It's basically plug in all the concentrations at equilibrium, and you can find the Kc that way. All right. So just let me know if you're getting the same number. Good. Somebody got that. All right. Good. I just want to make sure that when I do this on my calculator, so if you put in 2.34 squared, I don't know, like that, divided by 3.12, this is where it gets tricky. Because if you put a times here, it's going to give you the wrong number unless you put parentheses here. Or the way I like to do it, because I always do the fewest keystrokes, I put another divided by. And you divide by everything that's in the denominator. If you put this times here without these parentheses, then the order of operations, which the calculator knows very well, says, okay, I'm dividing by 3.12, I'm getting an answer, and then I'm going to multiply that whole thing by the 1.5 cubed. So unless you put a parentheses around this stuff in the denominator, or 2 divide signs, one before each number, you might not get the wrong answer. You might get the wrong answer. All right, I don't know if that helped anybody, but I don't want to see that. I don't want people getting wrong answers because they don't know how to use their calculator at this point. You know, if you're having a problem with this, you should hang around after class and I will go over with you on your calculator. All right. All right, so I'm going to skip type 2. We're going to do that after. The next problem type, equilibrium problem type that I'd like to go over is type 3. It's a very basic type. It's one of the easier types of problems. So if you're given the value of the equilibrium constant, so you're given K, okay, the value, and all but one of the concentrations of everything at equilibrium, all but one of the equilibrium concentrations, you can find the concentration of the one that wasn't given. And I use this sort of hypothetical reaction. Z2 goes to 2Z here. And so in the equilibrium mixture, in the reaction mixture, which we've said it's at equilibrium, we know that the concentration of Z is 0.93 molar. And we've also been told that the value of K, Kc, I could call it, is 5. So what we have to do here is write the equilibrium expression as Z squared over Z2. All right, now I know what this one is, but I want to know what this one is. This was the one I don't know. So I'm just going to cross multiply Z2 times Kc equals Z squared. And the one I'm trying to solve for is the Z2. So it's just Z squared over KC. Or if you could plug in the number here and you could plug in this number here, and then you could solve it any way you want. But this is the way I do it. I always solve for the thing first and then plug in later. So this would be, oh, I'm sorry. This isn't 0.93. What? Why do I have that on there? Where did I get that number from? Sorry. Wow. Wait. Oh, maybe I'm on the wrong page here. Oh, I am on the wrong page. It is 0.93. All right. So this is 0.93 squared over 5, which is 0.17. So that is the concentration of the one we didn't have. All right. So when you have, all but one of the equilibrium, of the concentrations at equilibrium, just formulate the Kc expression like that, putting the stoichiometric powers and everything. Even if you have more than one reactant and product, you just have to put all the products on top, all the reactants on the bottom with the stoichiometric powers. And then put in everything you know and solve for the one you don't know. Okay. All right, so that's type 3. I'm going to talk about type 5. Okay, here's type 5. One of these days, I'm going to rewrite these handouts and put them in the right order, but that's okay. So type 5 actually has 2 parts. And the first part is kind of the easier part. And the second part is harder, and we're not going to cover that yet. So given K and the concentrations of all reactants and products, determine if the reaction is at equilibrium. We already know how to do that, right? We did that in the problem I just went over with you. Where we had, the 4 and the 1 and the 1, and we put them in and we found out that QC was the same as KC. So C, if the reaction is at equilibrium, that would mean if that ratio equals, if QC equals KC. If it is not, determine which way the reaction will go. Well, we've seen a bunch about that too. If QC is less than KC, the reaction goes forward. If QC is greater than KC, the reaction goes in reverse. Okay, this is part 2. In the hardest version of this problem, determine the equilibrium concentrations. We're not doing that yet, okay? But you should be able to do the first part of the type 5 problem, which is to figure out if this is at equilibrium and to figure out the direction. So QC, because you're not told if it's at equilibrium, so you can't say KC. QC is Z squared over, Z squared over Z2. And that's 2 squared over, well, they have the same concentration. Well, that's easy. 2 squared over 2 is 4 over 2, which is 2. All right. KC is equal to 5. Okay. So QC is less than KC. So which way will the reaction go? Yes, forward. So that's it for the first part. That's the easy part of a type 5 problem. Okay. So now I'm going to show you a type 2 problem. Type 2 is like a level up in difficulty. We've just leveled up. Okay. Type 2. Okay, so this is a type 2 problem now. if you're given the initial concentrations of everything and one equilibrium concentration, you should be able to find the other concentrations and calculate the value of the equilibrium constant. All right, let me show you how this works. Okay, so we have a real reaction here, and the N2 plus F2 reaction to form NF3. Okay, and here are the initial concentrations. Now, I put an I here for initial. This is going to be a new type of ICE problem, ICEE for equilibrium. Just like if you were in my class in Chem 103, although I haven't taught it for a while, I teach that C is the change. So we have initial change, and then instead of end, now that we're doing equilibrium, we know that the end is not going to completion. We know it's equilibrium. Okay, so, well, we're given the initial concentrations, and this is what you have to do to handle this type of problem. Given these initial concentrations, you know one concentration at the end, but the best way to handle this problem is to do an old let X equal, all right? So what I'm gonna, so what we need to figure out is how much of each of these things reacts. Because then we could take the amount, for example, for nitrogen that reacts away and subtract it, and we'll have the amount that's left. Same with F3 or F2, I mean. So I'm going to say let X equal the concentration of N2 that reacts away. Okay, N2 is a reactant, so it's going to go away. Its concentration is going to go down. Okay, so negative X is actually the change in the N2 concentration. It's negative because N2 is a reactant. And it's the only, at the beginning, there is no product. So we know the reaction is going to go forward. So I'm going to put a minus X under here. And then I know that at equilibrium, my concentration will be 0.2 minus X. So I'm writing it in terms of X, not because I need to find out the concentration of N2, because that's actually given. But that tells me that for the F2, okay, if we make X equal the change in the N2 concentration, then 3X is the change in the F2 concentration, or really minus 3X because it's going away. So you see, by putting minus 3X here, it's telling you that 3 times the amount of N2 that goes away is the amount of F2 that goes away. And I know that because I have a 1-to-3 ratio there. So whatever this coefficient is, that's what ends up going in front of the X. So if negative 3X is the change in the F2 concentration, then plus 2X will be the change in the NF3 concentration. And so I can write that at equilibrium, my concentration of F2 is going to be what it was initially, and then the change, which is really a subtraction because it's products going away. Whereas here for the NF3, it starts at 0 and becomes 2X. So what I have when I do this clever way like this is I have my equilibrium concentrations in terms of X. But the beauty of the type 2 problem is that I actually know what one of them is. So I know that 0.080 molar is 0.2 minus X. And this allows me to solve for X by solving this equation. Okay? It's probably a little dense there, but you get used to it, really. So I have this equation, and what I'm going to do is move the X over to the other side. I don't like a negative x, so this is 0.080 plus x equals 0.2. Now I'm going to subtract 0.080 from both sides. And that gives me x equals 0.2 minus 0.080, which is 0.120 molar. Well, that's not really any of these concentrations because I have to find out what, like I already know that the nitrogen concentration is 0.080, which is 0.2 minus x. But the F2 concentration, I don't know. And the F2 concentration is 0.5 minus 3x. So I can substitute in this for the x. And I get 0.5 minus 3 times 0.120, which comes out to 0.140, which is the F2 concentration. See why I said it was a level up in difficulty. What about the NF3 concentration? We go back and look here, we see that's 2x. So all we need to do is multiply x by 2. Okay. So now that I know what these concentrations are at equilibrium, I know the equilibrium concentrations. I was given one of them, right, the nitrogen, but I know that this is the concentration of NF3 squared over N2 to the 1, F2 to the 3. So it's 0.240 squared over, the F2 is 0.140. That has to be cubed. And the N2, which was given, was 0.08. Okay. Actually, I don't think it had a 0 there. And this comes out to 262, which I would write 2.6 times 10 to the 2. So that is a type 2 problem. Would you like me to go over that one again? Anybody? Everyone's okay with that? All right.
Actually, I think I have a question.
Yes, please.
Sorry. So the last part when you were getting the NF3, actually no, when you were calculating the KC and how did you get the powers for each thing?
Oh, you go back to the reaction and you look at the stoichiometric coefficients. Yeah. The
Oh,
one guy.
thank you. Oops.
And also, I just want to say that whenever you have a problem like this, it's best to look at something that has a coefficient of 1 and do that one first, right? And call that the single x because it's like a 1 there, right? And then everything else will come into place once you have the one with the coefficient of 1. If you don't have something with a coefficient of 1, then I would say to start with anything and just put the coefficient here in front of that x. That'll be the best way to do it. Anyway, any other questions? Because that's pretty much what I wanted to tell you for today. If you want to ask me anything, you can hang around. Otherwise, I'm done. But I'll wait, see if there's any questions. Somebody sent me an email for class. I couldn't get back to you, but I'll write you later. Yeah, I'm going to send that exam out tonight or tomorrow morning, so be ready. Good luck. Have a great day, everyone.
Hey, Professor,
Hi.
when will be the next exam again? Sorry.
Sending it out tonight or tomorrow morning, and it's going to be due in a week from tomorrow.
Okay, cool. Thank you.